This next example comes out of section 6.1, reciprocal quotient and Pythagorean identities. Before we even get into some trigonometry here in section 6.1, I want to compare two equations, just equations in x. Looking at them, they both have some x squareds, they have some x's in them, so they look kind of similar. We could try to solve these things either algebraically or graphically. Maybe graphically might be a better picture representation of what I'm trying to get at here. If I graph y equals x squared minus 4, I get a parabola that looks something like that. If I graph negative 13 minus 6x, I'll get something, I guess, very steep. Something like this, and it actually touches that parabola somewhere. So we could say that there's actually a solution to that equation. We could, solve it algebraically to say x squared plus 6x plus 9 equals 0, bringing everything to one side, factor it, and I can see where I had a solution which was at negative 3, and I would have found the same intersection if I did it graphically. Looking at the other equation that I have here, I have y equals x plus 1 squared. If I decide to draw this, it's a parabola that's been moved over to the left a little bit, and if I draw x squared plus 2x plus 1, I get the exact same picture. In fact, if I try to solve that, I'll end up with a situation where 0 equals 0, or in other words, infinitely many solutions. Any number that I put in to this equation on the right here will satisfy it. If I put in x equals 5, you can try x equals 5, x equals negative 7, x equals 1.2, whatever number you want, and the left side and the right side will be the same. Whereas this equation on the left only was true for a certain value of x. This is the difference between an equation, something that is true sometimes, or may be true sometimes, or might even have a lot of answers, and something that is an identity, which is basically true for all values of x within the domain. So an identity, to define it, an identity we can define as an equation that's true for all values of x in the domain. If we look at something for trigonometry, if I look at sine x equals a half, just to choose a number or a function that we know fairly well, there are some answers to this. X equals pi over 6, x equals 5 pi over 6, and then any 2 pi after that, we could say, x equals 13 pi over 6, x equals 17 pi over 6, etc. Looking at that graphically, I have a sine graph, and I have y equals a half, and there are, in fact, infinitely many intersections, but I can't just say any value of x will satisfy that. That's different if I contrast it to something like tan x equals sine x over cos x. Now we're going to talk about that identity in particular soon, but we have mentioned it before, and it's true for all values of x as long as we're not talking about something that's undefined. So you could try x equals 1 degree, 2 radians, 78.9 radians, negative 56,000 degrees, as long as you weren't dividing by 0, by making, x can't equal a couple of things here. If we're looking in radians, x can't equal pi over 2, 3 pi over 2, etc. You have some non-permissible values, but you have every other value true for all other values of x. So hopefully you can see the difference between an equation like sine x equals a half and an equation that is an identity that's true for all values of x, like this one, tan x equals sine x over cos x.